Awesome. So why do I have Guinness on my slide? This is always like something that looks weird to people. Yes, I'm a bit of an alcoholic, I guess, but that's not the reason why I have Guinness on my slide. The reason I have Guinness on my slide is that actually Guinness is one of the earliest cases where mathematics was used in the industry. Actually, this was industrial manufacturing of beer. And Claude Guinness actually employed mathematicians, and specifically William Gusset, who was a mathematician that was, I think he studied at Oxford University, if I remember correctly. And he actually developed a statistical method of sampling. And what they did, they sampled batches of beer kegs. And this allowed them, using a very small number of samples, to determine whether or not the batch was okay or not. And this was later published. And Gusset actually had to publish under a pseudonym because Claude Guinness basically regarded his use of mathematics in industry as a trade secret. So he didn't allow Gusset to publish under his name. And this is why this test is today known as student t-test, because he actually published it under the name A Student, which is kind of a nice story, I think. So actually mathematics was used in manufacturing for a very long time, and it's something that we've been using in modern industry almost everywhere. But when you come and you talk to software engineers about mathematics, usually they're like, what? So this is why we're having this talk today. So without further ado, welcome to the Math of Reliability. My name is Avishai Ish-Shalom, Nukenberg on Twitter. You can look me up later if you want. There's a repository for this presentation, and also a companion IPython notebook with all the calculations and a bit more if anybody wants to go in and have a look. So feel free to do this afterwards. In my job, I'm a developer advocate for ScyllaDB, so it's worth saying a few words about ScyllaDB. ScyllaDB is the company behind the open source NoSQL database Scylla. It's a database that's compatible with Cassandra and DynamoDB, and when I say compatible, I mean it's API compatible. You can use the same drivers, same applications, no problem. It's a high-performance database, meaning that the throughput is much higher than that of Cassandra, but also it has very low latency, much lower than both Cassandra and DynamoDB. So highly recommended that you have a look if you're interested in having some kind of a high-performance database, distributed database. We have enterprise versions, of course, with support and everything, and also database as a service, Scylla Cloud. So I, again, highly recommend that you have a look. But this is not what you're here for. You're here to talk about mathematics. So usually when I talk to people about mathematics, this is the kind of response that I get. They're like, what, mathematics? No, this is hard, this is difficult, this is, we can't just wrap our heads around this. And actually, this is something that we should talk about, because it's really not true. So I have a friend who's a PhD in mathematics, and he actually told me once that the most common mistake that people do about mathematics is thinking that it's all about the formulas and about the numbers and stuff like that, and that's incorrect. Mathematics is actually about modeling the world and being explicit about your models and treating them in a very logical and consistent way. But that's all there is to it. It's about modeling the world and about making your assumptions behind the models explicit so you can reason about them. And if you're doing that, then you're doing mathematics already. So actually, a lot of us are actually doing mathematics and dealing with mathematics, even on our daily job. So there's no reason to be afraid of this. And you'll see as I go through the slides, this is not going to be like very complicated and scary and all that stuff. So now that we got this out of the way, let's give an example of why mathematics is useful for software and for software operations in general. So in this example, I took monitoring, and this is NAGIOS-LIKE ALERTS. It's basically a polling of some service. So it's a check that probes or samples some service to see if the service is alive. And basically it checks every 15 seconds. And if 4 consecutive checks have failed, then it would alert. Now, let's assume that the service is experiencing 40% error rate, and then the question is, what is the chances about us getting an alert, meaning 4 consecutive failures, over time? So, if we just take 4 consecutive attempts, the chance of getting, to hard or critical, which basically means failure, would be 2.6%. So 0.4 by the power of 4, basically. So if we start computing over time, how long before there's a good chance we're going to get an alert? So after half an hour, there's about 46% that we're not going to get any alert. After 1 hour, there's still about 21% that we're not going to get any alert. Even after 1.5 hours, an hour and a half, there's still about 10% that we won't get any alert. So what is the lesson here? The lesson here is that probing, basically checking every 15 seconds or something like that, or every minute, which is like what services like Pingdom, which is a very, very popular monitoring service, is doing, is very good for things that you expect to have hard failures, meaning like 100% error rate or close to it. But if your service, you're expected to have some kind of a soft failure, meaning maybe 10% error rate or something like that, which is actually a very severe failure for production services, then this kind of check is not very useful for you. And I've actually seen a lot of people use those kind of checks as even for the primary monitoring, because they didn't actually bother to make the calculations and see what are the chances of the alerting system actually catching those kind of problems. So now that we've seen an example of why mathematics is useful, let's actually dive into the mathematics of reliability. So when we're talking about the mathematics of reliability, the first question is, what is reliable? So we need some kind of a definition of reliable, and this turns out to be much more problematic than most people assume. So we have a lot of industry standard definitions, like 4 nines, or mean time between failures, or failures per year, or quality of service, and of course SLA, which is basically a legal document. But the problem with all of those definitions are that they're not enough, because in order to define reliable, basically that means the lack of failure, which means that we need to define what failure is. And when you ask an engineer, this is the kind of answer that you're going to get. Failure means a system operating outside of specified parameters, which is like really great, but it's kind of problematic as well. Why? Because if your users are complaining, then no one cares about the specifications of the parameters. So basically what this means is that you don't get to decide what failure is. Your users get to decide what failure is. And this means that we have to be very attentive to our users, and we need to redefine what failure means on a daily basis. It's basically an incremental definition that we keep updating almost on a daily basis sometimes. So this also means that failure is subjective, because let's say that I have a service and that has usually 27 milliseconds latency, and suddenly I have some problem and latency has shot up to 100 milliseconds. Is this failure? It depends. For one person, this might be a failure. For another person, this is okay. So failure is really subjective, and sometimes we need to make business decisions on what is acceptable to us, or from our subjective point of view, whether this is a failure or not. Now, when we talk about monitoring, there's a few possible states that we have to think about. And when I say monitoring, we need to think about this in terms of measurement. Monitoring is basically making a measurement whether your system is in a certain state. And every measurement has a few possible states. So the obvious ones would be, this thing is working okay according to our criteria, or it's failing, meaning it's not working according to our criteria. But there are more possible states that usually people don't think about. For example, unknown. Maybe the check has failed. Maybe the result is inconclusive. And this is something that also has to be modeled, and a lot of monitoring systems actually get this wrong. And when the system doesn't know what the answer is, it should present a known, but instead it's presenting a failure. And there is another very nuanced state, which is fuzzy. So what does fuzzy mean? Think about clocks. how do you monitor a clock? You basically compare it to another clock. But if you have two clocks that don't agree with each other, which is the correct value? This is a fuzzy state. This is a state where it's not clear what okay actually means. So we need to treat it in a different way. Now, finally, we need to remember that the absence of evidence is not evidence of absence. And this means that the absence of alert does not mean that the system is working properly. It could mean that your monitor has failed. It could mean that the checks have failed. It could mean that we just don't know what the situation is. So this is something that we're going to come back to in a bit when we talk about the mathematics of measurements. Now, let's talk about failure. So when we talk about failure, we have a lot of reliability measures for the parts of the systems that we use. It could be hardware. Usually it means hardware. So we've got some stuff like mean time between failures, or which is like years per failure. This is usually the numbers that we quote. Failures per year, which is usually denoted as lambda. Failure rate or probability of failure in 1 year, and so on, and so on, and so on. And those all of those numbers relates to each other. And for example, if you take a hard drive and you look at the MTBF of the hard drive, you would see something like MTBF of 30 years, which means basically that this hard drive can operate for 30 years. Now, here's an interesting question for you. Given that no one has actually used hard drives for 30 years, how do we know that the mean time between failures of a hard drive is 30 years, right? Especially if it's a new drive that we just shipped into the market and it's been in the market for, let's say, half a year. How do we know that the MTBF is 30 years? So I'm just going to answer. What they do is they take a bunch of hard drives. They take, let's say, 1,000 hard drives, and they put them in a lab, and they put significant workload on them, and they run them for, let's say, 3 or 4 or 5 months. And from that, they extrapolate, and they get those kind of calculations. But this is kind of a very interesting and important point, that what they do is they extrapolate from the space dimension of using a lot of hard drives to the time dimension of a single hard drive operating for many years. And this is important because all statistics are actually only meaningful when we look at groups. They're not really meaningful when we look at them in the context of a single device or a single object. So when we talk about statistics, it's important to differentiate between two very different situations. One is statistical independence, or statistically independent failures, and the other would be statistically dependent failures. So statistically independent failures would be something like hard drives failing because of some mechanical malfunction that is unrelated to manufacturing and unrelated to the operating environment. And this happens all the time, of course. Or EC2 instances rebooting for some unknown reason. That's also usually a statistically independent failure. Now, when we talk about statistically independent events, there's something called the hot hand fallacy, which is basically, think about a gambler that goes to a casino and starts gambling, and the gambler is winning for some reason, just at random. And then after winning a couple of times, it's like, oh, I have a hot hand. I'm probably going to win for the rest of the day. So the gamblers start taking more and more risks. And this actually, you see this a lot in more operations when someone tells you this system is safe because it hasn't failed yet. So that basically means that he's believing the hot hand fallacy, because the fact that your system hasn't failed yet doesn't mean that it's not going to fail, because every day is a statistically independent event. So actually the history of your system does not, you cannot infer from it into the future, into what's going to happen. And of course, the complementary fallacy to this is the gambler's fallacy, which is something like, okay, all the results so far have been black. I should bet on red because, there's a good chance that now I'm going to get red, because what are the chances that, it's going to be black all day? Or, I flipped a coin and I got heads 5 times. It has to be tails now, because what are the chances of getting 5 or 10 heads? And actually, every coin toss is a statistically independent event. So again, the history does not, you cannot infer from it about the future. It doesn't actually say anything. And the nuance here is that looking at the group of events and looking at the singular event is something completely different, and you actually need to compute it in a very different way because it's not statistically dependent. So the lesson here is that past performance does not predict future performance, and this is a mistake that a lot of people do when it comes to reliability of their systems, because they think that just because their system has not failed yet, it means that it's safe, and that's definitely not what it means. Now, the mathematics of statistically independent events, we can actually model this in a couple of ways. So first of all, we have what is called serial reliability. Serial reliability basically means that if we have a couple of components that are connected in series, meaning that all of them have to work, then the probability of them working, or the reliability, if you will, is basically the multiplication of the probabilities. Okay, it's a pretty simple formula. So let's take a system like that. Let's take a system that's composed of 3 parts, part R1, R2, and R3, okay, and they all have, the different reliability values, or in this case, probability of working, okay. So let's, we have, one of them has 2 nines, the other one's like 3.5 nines, and of course one of them would be 1.5 nines, okay. So what would be the overall reliability of the system? It would be 0.936, which is not a lot, but this is what we have. And you would notice that the reliability of the system is actually lower than the weakest part of the system. Now, let's try and improve different parts of the system. So if we improve the most reliable component, we get some improvement, but it's not a lot. If we improve part number 2, we get a bigger improvement, but still not a lot. But if we improve component number 3, we actually get the biggest improvement in the overall reliability of the system. And the lesson here is that the best improvement in a system that has serial reliability, meaning that it depends on all of the parts, is to improve the part which is the least reliable, because actually the system depends on the weakest link in the system. Now, often what we do is we use clusters, and in clusters we can actually allow some of the system to fail. So let's say that we have a cluster of 10 identical servers, and we can actually tolerate the failure of a few of the servers without the overall reliability of the system being impacted. And the mathematics for this is a little bit different. So when we have a redundant system, this is the formula basically, and those are weird parentheses, those are what are known as the Poisson brackets. You can look it up afterwards. It's not a very complicated formula, but I've computed the numbers for you, so you don't have to worry about this. So in a redundant system, let's say that we have 10 components, and we can suffer up to 2 failures, meaning let's say 2 failed servers without the overall system being down. You can see that the overall improvement is much larger. Okay, so remember when we improved the part with the least reliability in the serial system, we got something like 3.5 improvement. Here, even for improving not reliable part, we get 4.5%. When we improved from 1.5 nines to 2 nines, then we get 88.7% improvement, which is really good, actually. So having this kind of parallel reliability is the cheapest way of improving your reliability. So basically, redundancy allows you to have a very reliable system very cheaply. And this is the reason why we use clusters, definitely today in the cloud, but also in many other cases, because it's the cheapest way of improving the reliability of our systems. Now, of course, we want to see how this is impacted by changing the size of the cluster. So let's take a cluster with 10 components, and it can suffer 1 failure. And you would notice that the overhead in this case is 10% because you actually need to over-provision by a single server. Now, in this case, the reliability of the overall system would actually be lower than the reliability of the single server. So actually, in this case, it would make more sense to use a single server, not 10 redundant servers. But if we increase the ability of the system to absorb failure to 2 servers, then yes, we need to have more overhead. We need to have 20% overcapacity, but the reliability of the system is improved beyond that of a single server to 0.99 almost 2 nines. Now, if we continue with this, let's say that we take 100 servers and we can absorb 5% failure, then you notice that the reliability of the system is actually much lower than that of a single server. And the reason for this is that there's a very large chance that any server would fail. So with one server, we know the probability of failure. When we have a very large number of servers, then for each of them there's this chance of failure. So a chance of at least one failure is actually higher when we have a group. So you need to have high redundancy. So if we start increasing the number of let's say the number of servers that can fail, then we start getting our reliability back. And as you can see, with 9% overhead, we've already achieved reliability greater than that of a single server. Okay, so the lesson here is that, and we can increase it further. The lesson here is that, first of all, not enough redundancy will make your redundancy lower, your reliability lower than that of a single server, but also that when you use larger and larger clusters, you can actually be more cost effective because you can use a cluster with lower and lower overhead. And this is why companies like Google and Facebook actually prefer to have very large fleets of servers, because the ROI on larger fleet is higher. You can have lower overhead than with a small number of servers. This also means that the N+1 rule that many people use is only true for very small clusters. And if you use very large clusters, then you actually have to do this kind of computation and to realize what overhead you need to have in order to achieve a certain reliability. Now, when we talk about statistically dependent failures as opposed to statistically independent failures, so we assumed that the failure of a single server does not impact other servers, but unfortunately this is not the case for many systems. For example, if a server fails, then the load that should have gone to that server is going to spread on the rest of the system. And if the system is close to the edge, this might actually cause more servers to fail, especially if the failure originally was caused by overload. So in many cases, the fact that you have shared workload means that the failures are actually correlated. And this can also happen because those servers share code, or they use them on shared infrastructure. So if you have a problem in a certain availability zone in Amazon, for example, then this is going to be a correlated failure, and all of the servers in that region, in that zone, are going to be affected. And the mathematics for statistically dependent failures is very, very different, because actually the failure of one component actually increases the chances of other components failing as well. So in this case, redundancy would not help you. And to protect against those kind of failures, what we do often is we use components that are different on purpose. For example, many times we use hardware that has different firmware versions, or we buy disks from different batches, and so on, to protect against correlated failures. Another good example is running clocks that are unsynchronized, or machines that have slightly different sizes, or multi-cloud. That's another example. Now, let's talk about, what is this? Let's talk about the lesson here. The lesson is that backup and operational subsystems should avoid coupling with the primaries. Why? Because they might have statistically dependent failures. And if you take databases, for example, this is very common in databases, because when your database fails, let's say because it has some bad data, then if you're replicating to another database, then that database would fail immediately after. And likewise, if some kind of query is overloading the database, when you fail to the secondary, then the secondary will fail as well. And this is also true for clusters of application servers and so on, so on, so on. So when you have backups or operational subsystems, you want to avoid coupling. And this can be done in a number of ways. You can you can delay replication. You can make sure that the data set is different somehow. It's running a different software version, so on, so on, so on, like what I've mentioned, to protect against correlated failures. Now, here's a pop quiz. Let's say that we have a breathalyzer, and the breathalyzer detects all drunk people, meaning that it doesn't have any false negatives, but it does have 5% false positives, meaning that in 5% of cases, it will show someone who's not drunk as drunk. And only one out of 1,000 drivers is actually drunk. And the police stops drivers at random and checks them with a breathalyzer. And a driver will stop, and the breathalyzer shows that the driver is drunk. So what's the probability of the driver actually being drunk? So I'll give you 20 seconds to think about this. So what would be the probability of the driver being drunk? So if you answered 95%, you have fallen for the base rate fallacy. The correct answer is about 2% chance probability that the driver was actually drunk. And you can actually modify this question and change breathalyzer for COVID test, for example, or whatever other medical test that you want. It will still be same mathematics and same answer. And this surprises people. How come that the test showed us that this person was drunk, but actually there's a very low chance of this person being drunk? So here's the explanation. If we actually tested 1,000 drivers, okay, like we took a larger sample, one person would be drunk because this is the base rate of drunk people in the population. And the breathalyzer would indeed show us that this person is drunk because it doesn't have any false and negatives. But 50 people will turn out to be, you will test falsely as drunk because we have 5% false positives. So the base rate, the rate between the true drunk people and the falsely detected people, drunk people, is about 50-1, which is about 2%. So the problem here is that the base rate of drunk people is very low compared to the noise, which is the false positive rate of the breathalyzer. And if you think about this in the context of medical tests, then you would realize that if you went to the doctor and the doctor told you, okay, listen, you have you tested positive for cancer, that doesn't mean you have cancer. Actually, it might be that there's still a very low chance of you having cancer because the test has false positives. And this is why we always test twice or even 3 times before we begin some kind of treatment that is potentially life-threatening. Now, going back to IT, think about database monitoring and active standby failovers. So if we have a pair of databases like MySQL or Postgre, then often we would have an active and a standby, and we would have some external system that would check the active database, and when it fails, when it detects a failure, it would automatically fail over to the standby. Now, the problem is that this system, of course, cannot be 100% reliable, and it has some probability of detecting the active data, the primary, as failed. So even if it's a low probability, let's say 2%, okay, 5% false positive, according to the math we've just seen, there's actually very small probability of this failure being justified, this failover being justified. So it turns out that a lot of the automatic failovers from primaries to standbys, to secondaries, are erroneous. They have been done not because the database has failed, but because monitoring has falsely detected failure. And of course, this would not be an issue if those standbys would be harmless. But unfortunately, in many cases, those failures can cause databases to go out of sync, or they can cause data corruption issues, or data loss, or they can create consistency problems with the clients and failed transactions and so on. So this is actually a very big problem. So what can we do? Some people disable automatic failover. Some people work very hard on their monitoring or delay failover to reduce the amount of false positives, or, which is what I would advise you to do, is use a database like Scylla or Cassandra or another database that is active, and it doesn't matter which node you talk to. This is the normal state of the database, and then failover is no longer a problem. Of course, it's a trade-off. You have to trade off something. So usually this means working with a different consistency model, but this is a subject for a different talk. Now let's talk about microservices. So microservices have a lot of dependencies. Usually when you have a service, it talks to a bunch of other services, and this service potentially talks to a bunch of other services, and so on and so on and so on. And computing the reliability of a microservices system is very interesting. So let's suppose that we have a microservice whose native reliability is 2 nines, which is nice. And this service talks to 3 other services that also have 2 nines availability. So because it needs all of those services to operate, it depends on them, basically. This is a case of serial reliability. We can compute the overall reliability of this system, and you can see that it has reduced to about 1.5 nines, to 0.96. Why? Because the failure of any dependency would fail the service. But those services, in turn, also depend on more services, which also have 0.99 reliability. So the second layer would now have 0.96, and the upper layer would have 8.8. And this goes on and on and on, the more layers you add. So the problem with microservices is that the deeper the stack, the more services your call graph spans, the lower your reliability will be. And actually it reduces very, very quickly. So what can you do? What Netflix has done, and many other companies have followed suit and embraced this pattern, is use something called circuit breakers, which basically means that when you detect a failed dependency, you treat it as a soft dependency, and you cut it off, and you start giving out some kind of default response, or you terminate early, or you use a response from cache, or something like that. And this is the only way in which you can maintain reasonable reliability when you have a deep call graph, or when you have many dependencies that in turn have many other dependencies. Now let's talk a little bit about queuing. Now queuing theory is something that is very important for software engineers, and I actually have a different talk about specifically about queuing theory, and I urge you to look at it, or many other people have spoken about this as well. But one of the most important results from queuing theory is the relation between latency and the utilization of a system. So this is a graph of a simple system that has, let's say, one server, but actually most of the queuing systems behave in this manner. Maybe the graph is a little bit different, but the shape, the overall shape is the same. And what you can see in this graph is that the x-axis, this one, denotes utilization. And as you approach 100% utilization of the system, latency starts to shoot up. And it shoots up in a nonlinear fashion. So when you start approaching 70% utilization, you're already going to experience 200% latency overhead, meaning that if your system had 10 millisecond latency, your clients are going to experience 20 milliseconds latency because of queuing. And as you approach 100% utilization, it's going to shoot up very quickly to 100 milliseconds, 500 milliseconds, and even more, causing an outage, basically. And this is something that a lot of people are unaware of. And actually, in many systems that I've seen, they had to have very, very, very large over-provisioned clusters because of queuing, because most of the latency was actually due to queuing. So I highly recommend that you look at queuing theory and learn about it to see how your system behaves. Now, this relates to throttling, of course, because you don't want to have your system running at too high utilization, because this is basically going to increase your latency. So what do? We load shed and we throttle, which basically means that we're not willing to accept any more connections than the system can take without increasing utilization too much. Now, the problem is that when we have microservices and we have deep stacks of services talking to each other, one of those services down at the bottom of the stack, or maybe the database down at the bottom of the stack, might be overloaded. And the top of the system does not notice and keeps accepting more and more traffic into the system, potentially causing an overload and causing latency to rise due to queuing, as we've seen. So what can we do? What we can do is we can introduce a queue in the middle, and usually we already have a queue in the middle. So if you think about thread pools, every thread pool has a queue attached to it. So we already have queues for most of our services. If not in thread pools, then the socket would have a queue. So what we can do is we can limit the size of this queue, and then we can apply back pressure. When the queue fills up, we can start sending responses to the top part of the system, saying, listen, I'm overloaded, don't send any more traffic. And actually, most of the protocols that we use already support this. TCP has TCP back pressure built in, HTTP have 503 responses, and there's actually more than one HTTP overload response. There's, I think, 4.8 something, I forget the number, which also means overload. And basically, this is a way to signal the top parts of your system, stop sending any more traffic, and they would in turn, pass the back pressure backwards and tell, the client, don't send more traffic, I'm overloaded, and eventually the system will balance out. And this is basically the concept of back pressure. Now, another interesting result in queuing theory is known as Little's law. And Little's law is actually very intuitive. It basically means that the number of clients in the system, or concurrency, equals the arrival rate, which is throughput, times the wait time, which is the latency in the system. And this is very intuitive. We've all used this rule in many cases, but actually it was very hard to prove mathematically because this rule is universal. This law is universal, and it applies to any open system. And there's another version for closed systems which looks similar. Now, understanding how to use this law is very important because it's very useful both in system design and analysis. So I'm going to give an example of this. So let's say that we have a load balancer, and this load balancer is attached to a number of servers. And one very common algorithm for load balancers to spread traffic is known as list connections. Well, the load balancer would choose the next server based on the amount of connections this server already received, and it would try to balance the traffic between servers such that all servers would have a similar number of connections at a single instant of time. Now, let's assume that one of the servers failed. So when a server fails, let's say that lost connection with the database, it would start with returning errors very, very fast. Let's say 10 times faster or 100 times faster than it normally would. So let's say that the latency of every server in the system was on average 100 milliseconds. And then the failed server has 1 millisecond latency. It would return errors very fast. What we can see from Little's law is that the throughput of that server, or actually the ratio between throughput of a failed server and the ratio of a normal server would be the same as the ratio, the inverse ratio of the latencies. So if this server has 1% latency from the normal servers, it means it would have 100 times more traffic. So in this kind of system, actually we would have an outage because this single server that is running so much faster would start getting 100 times more throughput than all of the other servers. And basically you can get to 90-something% error rate from a single failed server. Now, this surprises many people because the whole point of clusters is that a single failed server will not have such a big impact on the overall reliability of the system. So what can we do against this? There's a couple of solutions. The obvious one would be not use list connections, but use some other algorithm like round robin or random or something like that. But even when using list connections, you can just limit the throughput of a single server. You can throttle it and if you know that the normal rate for this server is 1,000 requests per second, then you can throttle it at, let's say, 1,500 requests per second. That's one way to fix this. And another is to have some independent health check that would take this server off the load balancer pool as soon as possible, and many load balancers already do this anyway. Now, the final topic I want to talk about is feedback loops. So what is a feedback loop? So I'll give an example. As an example, think about mobile devices or mobile app, and this mobile app tries to connect to a server, and maybe it's a chat application, and it has some kind of long-lasting connection with the server, and suddenly this server experiences some network hiccup, and all of the clients disconnect. Now, what they would do normally is they would retry and reconnect to the server. Now, think about this. If you have 10 million clients which are disconnected and are trying to reconnect to the server almost simultaneously, what would happen? Even a very scalable load balancer would not be able to reopen 10 million connections at the same time. So at least some of them will not get service. And what will they do when they don't get service? They will retry again. And usually what people do is they have a static value for the retry timeout. So they would retry again, all of them together, and of course they would hammer the load balancer again and won't be able to connect. And then they would retry again, and again they would hammer the load balancer and won't be able to connect. And this is basically a feedback loop that causes more and more downtime. So actually we've seen this in many cases, and what we can do is we can use backoffs and cooldowns. So when you have retries, always make sure that you're not using a static value. You're using either a value that has some kind of random, random play interval, or basically has a cooldown, which means that maybe the first retry would be after 10 seconds, and then the second one would be after 20 seconds, and so on, so on, so on, so that eventually this feedback loop will be able to relax and service will resume working as normally. Now, it's important to remember that although we have all of those fancy formulas and fancy mathematics for reliability, reliability is ultimately everyone's responsibility. It's kind of a socio-technical problem. It's not only a technical problem. And as we've mentioned, it's the weakest link that breaks systems. So it's everyone's responsibility, and everyone has to care about the reliability of the system, because you never know which part of the system is the one that's going to break. So thank you very much. And if you're not going to run away now, then I will talk to you a second time, and we can talk about mathematics much more. If you have any questions, I'm going to be in the chat. I'll be happy to chat about mathematics and Scylla and databases and everything else that you are interested in. Thank you. Ooh, I should probably turn the light on. I can't hear you. Hello? What is going on? So what do you think?
Is it working now?
Yeah, now I hear you.
My system apparently does this fairly often, but if I leave and then come back, it doesn't work. So I have to actually leave all the way out and come back in.
I thought it was a problem on my side.
Nope, I can hear you fine, but
Yeah.
okay. I don't see that there's any questions in the Q&A or any in the chat. Thank you for the talk. It was educational, quite educational. I appreciate it. So, anybody have any questions? I know we're a bit over, so but the next talk in this track got canceled yesterday, so we'll be back at what did I say, 1710 or something like that, 1710 UTC.
Okay.
So, okay.
Presentation will be available later as PDF, not PowerPoint, because this is on Reveal.js, so I can't convert it to PowerPoint. Sorry.
That's okay. I prefer the the PDF anyway. So
Yeah. But actually, there's a summary. So I actually linked to this at the beginning. I'm also going to put the link for the repository. And there's a NiPython notebook with a bunch of examples and calculations there. If people are interested, then go ahead. None of this stuff is very complicated in any way. It's just that it's yeah. So the thing is just that people mostly just don't stop to do the calculations. It's not like very complex mathematics.
Right. Okay. People, you start with maths and people run away.
Yeah.
As you said, as you did at the beginning. So yeah.
Which is part of the reason why I talk about this, because there's really no reason to be afraid of this. It sounds scary, but it's actually not.